Okay, so we might get started, guys. So I'm Brett Hallam. I've actually come through this whole program at UNSW. I was one of, I think, the 5th group of students to go through this degree program. So I started in 2004. And this course number has actually changed since I went through. It was PV 2020 or Solar 2020. It's nice to see that there's been some consistency. 3507 is still the solar cell program, and then 3540 I think should be applied PV, but there has been. Oh, that's changed as well. Okay, yeah. So I've been lucky enough to go through this whole program, then follow on with a PhD, and now a researcher here. So I'll continue on. So the big transition for the industry of what's happening, like Bram just mentioned, is this evolution to the PERC technology, and really it's just to displace the conventional ALBSF. That's really the only trend of what I'll be focusing on for the rest. This apparent suggested, I guess, transition maybe towards some of the N-type technologies. I think that's been happening in the roadmaps for the last 5 years. We didn't have an evolution of the roadmaps, but it's a bit like the plating. It was always just, oh yeah, 5 years time, etc. The only real trend in the industry at the moment is this transition to PERC. So we're going to be looking at what happens with PERC in terms of the emitters and what's happening. But I'm going to go back a few slides here. So looking at this structure, even though Bram mentioned that structurally there's no difference on the front surface in terms of emitter and things like that, I'm going to put a question out to you. What happens when we change the voltage of the device? What will we need to consider? Anyone?
Would you need to consider the resistance?
Yes, exactly. So if we were to use exactly the same sheet resistance on the emitter, because we've changed the open circuit voltage, or more so the operating point of the solar cell, it'll actually change the series resistance within the device. So, and that's one important thing to consider. Basically, anytime we make a single change in our device, we potentially need to completely redesign the entire solar cell. So because we've now put the surface passivation on the back, we've reduced the surface recombination velocity, we increase the voltage, potentially we need to adjust the front surface slightly. So either changing the sheet resistance, bringing the fingers in close together to counteract what natural changes will occur for the series resistance, so to re-optimize the efficiency. But getting back to what is actually happening with the sheet resistance, it's always going up. It's been going up for the last 10 years pretty clearly, and a lot of this is we want to reduce the J0 of the emitters. So the emitters have different recombination. Bram highlighted the Auger recombination within the emitter. If you have a really heavily doped emitter, you have Auger recombination within that emitter due to all of these extra dopants. But then you've also got the surface effects like Bram mentioned, etc. Generally a higher doping is better to reduce the minority carrier concentration, but it all can affect this J0, the emitter's dark saturation current density. And generally we want to go to a low J0 recombination so we can get higher VOC and JSC potential. So that's what we're shifting towards, but that creates a lot of challenges for the metallisation and how we make the solar cell. So if, for example, we want to increase the sheet resistance to the emitter, what do we need to do to counteract the total series resistance of the devices? Any ideas? It's on the screen. Should be pretty easy. We need to put the fingers closer together. So, and another question, what's that going to do to the shading?
Increase the shading.
Yeah, so that's not a good thing. So what do we need to do to counteract that?
Change the finger design, the aspect ratio.
Yeah, yes, and that's typically what is happening in the industry. People are looking at thinner dimensions, trying to increase the aspect ratio of the contacts, etc. And yeah, so we need to increase or modify the metallisation process. Also from a J0 point of view, typically as we go to this, these higher sheet resistance, we might bring down the peak doping concentration. So that increases the minority carrier concentration, not good for a combination at the metal silicon interface. So a lot of the development, like Bram mentioned before, it's really come from the screen printing, screen printed paste manufacturers, and as well as from the screen printer tool manufacturers. And that's where a lot of these developments are coming from. And whilst we were really excited about our laser dope selective emitter technology, there's also been a lot of other selective emitter technologies, either I guess selective etch back, so screen printing the metal onto the solar cell potentially before nitride, then etching off some of the heavily doped silicon surrounding that, or a whole other range of processes, either screen printing a mask, say ink or wax, and then etching this to create this selective emitter, and then doing an aligned screen print process. Really, the industry is still going to be dominated by this homogeneous emitter. It's relatively cheap, it's very simple. All of these selective emitter technologies require typically extra steps and bring extra complexity, and the industry doesn't actually like that. The biggest technology in the industry is really standard screen print, full area, aluminium back surface field on multi. It's the cheapest and probably the simplest to make. So all of these extra complexities of going to these, say, selective ion implantation or other selective emitter technologies, they're not expected to come into the market in a great deal. And all of this means that as we change this emitter design to go to these high sheet resistance emitters, we need to change the way we do the screen printing, in particular the use of the metallisation pastes. So for the next 10 years, we're still expecting this homogeneous emitter to dominate the market. So looking at the actual screen printing technologies, so we're still using a technology which is thankfully still older than I am, developed in the 1970s. So, and that's what really dominates our industry, the same way as you screen print a t-shirt, we're just using metal. But there has certainly been a big trend to reduce the consumption of the silver, because that is quite a large cost potentially of the solar cells. We've got here the silver price over the last 100 years, and you'll see that there was a few years ago there was quite high prices, about $40 per kilogram, I think should be, I can't remember, or for the paste or whatever, or might be troy ounce, might be, yeah, troy ounce, yeah. Yeah, so it shot up quite high. That's actually come down now as there's been more silver become available. It's certainly part of the reason. So now it's down at 10. So those few years ago was when plating certainly looked exciting, because it could be potentially a lot cheaper by completely eliminating the silver on the front surface, going to a copper-based conductor, so using some of the plating technologies we've developed here. Unfortunately, once this silver price comes down, the financial advantages of shifting away from screen printing to other alternative technologies like plating, where they can use copper as the main conductor, have pretty much gone. So really the industry is not looking like it's going to have any significant portion of plating and these other base technologies. Certainly in the next, say, 5 years, it's going to be heavily dominated by screen printing. And one of the big reasons, like I've said, it's mature and simple. It's relatively extremely simple process in production. A lot of the science is in the pastes and the tools rather than the process requirements. So in talking about lowering the costs, one way we have is the lowering of the silver price. The other is the silver consumption. And this is the finger width of what's expected in the industry. So going from, say, 60 microns, which is pretty state-of-the-art for some of the tools now in production, and heading down towards 25 microns over the next 10 years. And do any of you know the rough width of fingers if you're using plating? Did you cover that in any of the lectures or from your other subjects? Yeah. So what would you expect as a rough finger width for plated contacts? Maybe someone up the back? No? Just chuck a number. Surely you know, Nick. Okay. It's about 25 microns. So, yeah, you can, if you're using a laser-based process, typically with the feature sizes from the laser focus, you're looking around maybe a 10 to 20 micron spot size, which pretty much determines the width of the opening. So as a minimum, you're looking at say 10 to 20 microns for a plated contact, but as you plate up to get the conductivity, it also plates out. So typically we're looking somewhere around this 20-25 microns. So then suddenly we're not necessarily going to get lower shading losses as we go to plated contacts from what's potentially achievable using the screen printing technologies. And now I was at a presentation given by DuPont and also one of the tool manufacturers, DEK, which has now been taken over by a larger body, ASM-AE, I think is the name for them. And they've demonstrated that they can print 35 micron wide lines for the silver front contacts. It may still be a little bit away from going into large scale production to do that. Typically they're doing a double print, so having a print on print basis so that they can print a narrow finger and then they can have a second process come over the top. Very, very good alignment, typically less than 10 microns, and to add some height to those fingers. But as you do that, potentially you need to change the screen material, so it needs to be a certain kind of screen. They're having challenges with some of the emulsions and the actual structure of the screens to maintain that over thousands and thousands of prints to keep these really high aspect ratio contacts. So that's the double print technology, and that if we improve the aspect ratio of the contacts, reduces the shading, then we can start to bring the fingers in closer, and so we get to reduce the series resistance, etc. There's another approach that you can go for dual print. So this is where we separate the metallisation process for the fingers and the bus bars. So the fingers we need to collect the electrons or the holes out of the solar cell. And for the bus bar, really that's just to conduct those carriers to the interconnection scheme. So there we don't actually need a metal silicon interface. It can be potentially floating. So it gives an option to have completely separate metallisation for the bus bars and fingers. So for the fingers we need a frit-based silver paste, so it penetrates through the silicon nitride during the firing, contacts the metal, whereas we can use a separate, whether it's silver or another conductor, just to float above the silicon nitride to carry the carriers. So this is a lot of the trend of what's happening in the industry. This graph is showing the latest generation of a paste by DuPont, so the PV19X series, is really going to help increase these aspect ratios. So they're looking, I think it's 30 micron dimensions across here. Actually, no, sorry, it might be shorter, but it's certainly getting down to 35 to 40 microns potential width. So they're getting pretty narrow. So companies like DuPont are putting a lot of emphasis onto the development of new pastes, and every year they're coming out with the next generation of pastes, and a lot of those developments in the paste are really what's driving the efficiencies up in the industry, as opposed to these very slight changes in solar cell architecture or otherwise. And what you can see is it can add positive changes to the distribution of efficiencies in the solar cell production. So this is just coming on the market now. In terms of going to lightly doped emitters, that also faces challenges, as I mentioned. This was probably not a perfect graph of what I was hoping to include, but basically it shows that as we reduce the surface concentration of phosphorus, you need to change how the paste is made to allow effective electrical contact to that doped surface, and reduce the J0 or maintain a relatively low J0 and not increase the series resistance or the contact resistance at the metal silicon interface too much. So they've had a whole range of paste developed over the last 5 to 10 years, going through this PV16, 17 and 18 series that allow contact to more lightly doped emitters. So now they're claiming towards, say, 120 ohms per square that they can contact. And as we do that, we can increase the VOC of the devices. And that's been most of the efficiency enhancements have come from these developments in the last 5 years. So another potential way to reduce on a module level now in terms of the metallisation is if we cut the cells in half. So after we've fully processed our solar cells, if we cut them in half, we halve our total current of the devices, and that reduces the series resistance by a factor of 4. So this is becoming apparent. Trina's world record module, I can't remember the efficiency of this module, was it 18, 19% or something, but it was certainly a world record. But they've basically chopped the cells in half and then put in, so rather than being a typical 72 cell module, 6x12, now it's got twice as many cells. Although I think I've seen some presentations saying it's still a 72 cell module, but rather it's a 72 wafer module that then they've chopped up to double number of cells. So it's one actual advantage of going to this. The problem is what's that going to do to our production sequence? What do we need to do? Any ideas?
If you cut the the wafer, you'd have to process it to make sure it's not damaged.
Typically it's not too bad in terms of the size, but certainly when we were making our pearl cells back in the 80s and 90s, the edge recombination is actually a significant issue, particularly at low illumination intensities. The problem is going towards the encapsulation process, they have to completely redesign their stringers because they're all designed on a, say, 6-inch or 5-inch scale. Now they've got to modify a lot of those tools, so that's adding some extra complexity. And you've also got extra interconnections for a whole module, so there's potential yield issues as well. So those are the main challenges of what's happening, but certainly they're expecting that this might become a way in the future to reduce the series resistance losses, and certainly a nice way to make some world record modules, because potentially these may have not even been 72 wafers. It could have been 144 different wafers, and they've just chose the best half of each or whatever. But certainly, nonetheless, it's an exciting result for the industry in the increases in the efficiency. Another a trend that's certainly becoming apparent is the increasing the number of bus bars on the solar cell. So as we increase the number of bus bars, we can potentially make the bus bars narrower, reduce their silver consumption, etc. Also relaxes some of the constraints on the fingers for how far the fingers have to conduct the carriers to get to the bus bar, etc. So we get increase fill factors and reduce the silver consumption. So the trend of the industry is certainly going towards 4 bus bars, potentially 5, but most of it looks like it's going to 4 bus bars. In the longer term, there's also a couple of other technology like floating bus bars, so what I mentioned with dual print, it's a way to at least reduce some of the metal silicon interface area. So that's going to become more important as we go to the higher efficiency solar cell structures. We only want a metal silicon interface where we need it, otherwise it's going to hurt the J0 of the device and then to reduce the voltage. The other is going to completely bus barless design. So we only, say, screen print fingers onto the solar cell, and then we use an interconnection process to effectively make bus bars on the surface. So I've got a picture here of Meyerberger's smart wire technology. So with a screen printed solar cell just with fingers, we have an encapsulant material which has these copper wires embedded in this encapsulant material. So during the lamination process, sandwich is made in the laminator, you heat it up, there's a certain reaction. Typically these wires are coated with, say, tin bismuth and alloys at very, very low temperatures. So then it can make the electrical contact to the fingers underneath. So this is one technology that's looking promising, although there's probably mixed reports over some of the costing. You might have a bit more information on that of the actual cost. And as an alternative, is it tin bismuth or tin indium?
Currently they use an indium alloy.
Yeah.
Indium is extremely expensive, so in order to make it more cost effective, they're trying to move to these.
Yeah. But the problem is as you change these alloys compositions, you change the potential melting temperature of them, and you have a certain range on what the EVAs or encapsulants, silicones, etc. can tolerate during this lamination process. So it gets quite complicated to integrate all of these processes together. But certainly that's one option that the industry is sort of moving towards. And also, I guess, there's also been some development with copper-based pastes as well, which could pose challenges. Typically, you don't want copper in the solar cell. So if it's the copper is above the silicon nitride, you need to make sure that the silicon nitride is going to be protective against the diffusion of copper into the silicon, etc. So as another aspect of what certainly becoming apparent in the industry is the need to look after the environmental impacts of PV. So one aspect is getting away from lead-based solders. So there's certainly a trend in going to lead-free solders for the screen printing process. Potentially, if we get rid of silver, going to electrically conductive adhesives, so more, I guess, polymer-based solutions, smart wire, and the elimination of toxic materials. And so when you start talking about that, you start to wonder, is the, say, first solar technology, which is based on calcium telluride, such a sensible? Cadmium is not a material that we really want getting into our waterways. So we need to start thinking about the materials, what are going into these solar cells, how stable long-term are these compounds. And also, after the lifespan of the solar panels, which are guaranteed for, say, 25 years, what do we do with the panels? We need to start looking at recycling the silver, the other materials within that, so that it is certainly a more sustainable industry. And that's certainly becoming apparent. So I guess for the next 5-10 years, the major shift is really to eliminate lead-based solders in the industry. So now we get on to the bulk improvements, and there's a couple of different areas of this. So there's been a lot of improvements around the wafer casting or crystallization methods, then as well as passivation and elimination of LID, and that's probably the most apparent the areas of what's happening at the moment. So one that Bram briefly touched on is this fluidized bed reactor, which was developed by REC. So an alternative to the purification to develop polysilicon than what has conventionally been done using the Siemens process. So this is very, very energy intensive. It's, from memory, it was like 110 kilowatt hours per kilogram of silicon, whatever. There have been some improvements to some of the later generation of the Siemens reactors to reduce, I think by maybe a factor of 4, the energy consumption in this process, but nonetheless it's still very, very energy intensive. Whereas with the FBR technology, it's looking at 80 to 90% reduction in energy, and it's also in line. So as the reaction takes place, you inject silane into this reactor, the granules of silicon after purified come out, so it's completely in line, whereas with the Siemens reactor it's a batch process, and ideally for high throughput processes you want them to be in line. Batch processing can slow things down. And this FBR technology is becoming, certainly emerging into the market. And it can as you change the size of these granules compared to generally these chunks of polysilicon that go into this casting process, it changes the packing density of what can go into these silicon casts. So it can have changes to the cost in that aspect as well. So in terms of the crystallization techniques, in terms of N-type versus P-type, you pretty much see that N-type here is this blue color, and that's up here. It's only a very, very small fraction of the ingot, the industry, about 5% at the moment. Everything else is this P-type multicrystalline, P-type mono-like, that's over here. It's basically just all P-type, and that's what the industry is using at the moment. There's always this suggestion that N-type is going to become more prevalent in the industry, but this seems to be getting shifted back all the time. And some of the recent developments with the P-type technologies will really question these trends of what's happening. A lot of the reasons for avoiding P-type due to light-induced degradation don't seem to be so much of an issue now with what's happening in the industry. And one thing about the P-type material is inherently it's a simpler processing sequence to make the P-type solar cells. N-type, as soon as you go to N-type, typically you need to go to boron diffusions, high temperature processes, very, very long, and you can't take low quality silicon through those processes. Multi doesn't like going up to high temperatures for very long. And there's also some other recombination active defects that can form during these really high temperature processes. And for the P-type technologies, we naturally have to do a phosphorus diffusion, and that's a way to, whilst we form this emitter, we can improve the bulk quality of the silicon through the gettering of impurities, say iron or metallic impurities that get into the silicon. They can move towards this heavily doped region where they don't hurt the performance so much. So there's this, natural healing of the silicon in some of these P-type technologies. So in terms of the actual crystallization, if we take a conventional kind of multicrystalline silicon wafer made into a screen print solar cell, relatively large grains but very, very variable. And the industry's moved away from that conventional, you just chuck the silicon in there, let it solidify as it wants to. So a few years ago they went to this seeded cast process. So if you look just at this image on the left, what do you notice about the difference between these two?
Is that one big grain in the middle?
Yeah. It's a seeded material, so during this casting process they take a monocrystalline silicon wafer or a chunk of silicon, and these cover the bottom of the cast. Then when they grow these, our cast, they heat up the silicon cast from the top, melts all the silicon, melts part of this seed, but they stop the heating process before you've dissolved all the seed. Then as you let it cool from the bottom up, it takes on the orientation of this seed at the bottom. So essentially you can grow monocrystalline silicon during a casting process. Unfortunately, it doesn't always work out perfectly, and you can get some of these multicrystalline other grain orientations around the edges. And apart from being single versus multicrystalline, what's an advantage of the casting process in terms of the concentration of oxygen? Have you covered that in any of your courses so far? Sorry, I can't. Exactly. Yeah, so that's one advantage of this technology. Potentially, and BP developed this technology a few years ago. They had patents on it, their cast mono process, that they can grow single crystalline silicon but potentially avoid LID, lower oxygen concentrations, and therefore lower boron oxygen. So it was looking pretty exciting that potentially this material can be higher quality than CZ silicon, which is more expensive to make. The problem is it doesn't always stay monocrystalline. And if you have a look at this PL image over here, what do you see? And this sort of shows the rough quality.
It's a lot of dark areas, isn't it?
a lot of dark areas. These are dislocation clusters. So even though it's mostly single crystalline material, one of the problems they've found with this technology is that the grain boundaries which were in the multicrystalline silicon were actually a stress relief mechanism during the crystallization process. And once you take those grain boundaries out, you don't have that stress relief mechanism, and stress builds up throughout the process. So you get these dislocation clusters forming, and they generally grow in size and spread out through the cast as the casting process continues. And eventually the stress becomes too big that it'll go into these multicrystalline regions around the edge. And that's one important thing about this technology, is that non-uniform aesthetics. This overall sort of looks a bit more uniform. It's different shades of blue, etc., whereas this mostly looks black, and then you have this random bit of blue. Everyone's different, and some of the consumers don't like that. They think there's something wrong. So that's one, the aesthetics, and same as with these snail trails, even though they may not hurt the performance of the panels too much, industry wants an aesthetically pleasing product. So even though 5 years ago there was a massive hype in these roadmaps about this cast monosilicon, the industry has moved away from it, because to avoid the generation of these dislocation clusters, you have to reduce the thermal stress, so reduce the rate that you crystallize this material, and that reduces throughput and can increase the cost of the product. So what they've done, and I apologize, I don't have a photo of the actual the grain structure on this material, but you can sort of see it from this PL image. Most of the little lines are the grain boundaries here. And what do you notice about the size of the grains compared to the conventional, the multicrystalline silicon? Any ideas? Smaller. And it seems sort of counterintuitive that you want to get a high quality of silicon, and you're actually going to increase the number of grain boundaries which act as recombination sites, etc. But they've found that this is actually a much nicer way of crystallizing the silicon, can lead to higher performances. Because you'll see that the dislocation clusters are only very small, and there's not that many of them, because these grain boundaries act to eliminate the stress during the crystallization process, so they can minimize the generation of these dislocation clusters. And even though they have these grain boundaries, this is before they've given a passivation process during firing. For this crystallization process, they deliberately target certain orientation of grains in the silicon, and that they choose grains that are lower combination active in terms of their grain boundaries, so that either they won't hurt the solar cell performance too much, or they can be adequately passivated, say as by hydrogen, etc. So it can lead to more uniform quality of the silicon and higher bulk lifetimes, because in these grains, you actually, within the grain, you get very high lifetimes. It's actually quite impressive, and this is now set to dominate the industry. So the industry has moved completely away from the cast mono technology and shifting towards this, what they call high performance multi. I think I've covered everything there. Yeah, so then to go on to the mono silicon, it's still going to be dominated by CZ. So we've got blue CZ. The orange is a continuous CZ. So a normal CZ process is very much a batch process. So you melt a certain amount of silicon in a crucible, and then you start to crystallize the ingot. The volume of silicon in the melt goes down, etc. And there are certain challenges of this process, being batch. Every now and then you have to swap over to get a new crucible of silicon. The impurities during the monocrystalline silicon process segregate out into the melt. So it's sort of like a relatively good purification process for minimizing metal incorporation into the silicon. So iron, for example, for every silicon atom, only 1/1,000,000th of an iron atom will incorporate into the actual crystal. So that's great at the start of the ingot, but as you continue to grow the ingot, the impurities do build up, and Yeah, so you'll get relatively higher impurity concentrations, typically towards the last part of the ingot to solidify. Unfortunately, that also works for the dopants. And so you get this variation of dopant densities throughout this ingot. P-type, the boron atoms have a segregation coefficient of 0.8. So it means that it's a relatively uniform distribution of boron throughout the silicon. Phosphorus, so for the N-type technologies, lower segregation coefficient, so less phosphorus atoms are incorporated at the start of the process, but then they build up to more and more throughout it, and you get a larger variation in the resistivity and the dopant density of the materials. So that can make another challenge of these N-type technologies. And because as you change the resistivity, you'll change the electrical performance, JSE, VOC, etc. So the industry is moving towards a continuous CZ process, which can counteract some of those. It's a semi-inline process. As they grow the ingot, they have pretty much a fixed volume of molten silicon. They keep on adding new silicon into this melt, and they can start to counteract the variations in dopant densities if they change the percentage of phosphorus or boron that's going into this newly added material throughout the process. They can sort of eliminate some of the variations in certainly the dopant densities, but you can't do it forever, otherwise you're going to have too higher metallic impurity concentrations, so then they need to go to a new batch, etc. But that's certainly set to become more evident within the industry, and it should reduce the costs. But it's still relatively early days for this technology. The other big aspect of what's happening in the industry is to eliminate LID, so the carrier-induced degradation, or light-induced degradation as it's commonly referred to, particularly what happens in the boron-doped CZ due to the presence of boron oxygen. So this is a tool by Centrotherm that's been released, and there's a few different tools on the market now, and a lot of the manufacturers are taking up these tools to reduce the influence of light-induced degradation. So if we take a normal solar cell, this is a PERC solar cell, 20% efficiency, 20% straight off the production line. You put it under sunlight, it drops down 18.8% efficiency in this case. But there's a process with illumination and a temperature where you can recover permanently most of that efficiency loss. So we can eliminate a lot of the LID losses. And so with these kind of processes, P-type again becomes more appealing, because a lot of the reason in going for N-type technologies is the avoidance of the boron oxygen defect. So this tool is quoted as being able to recover about 80% of the efficiency losses due to LID, taking about 20 to 45 seconds, but it does depend on the solar cell architecture, the lifetime in the silicon, and I'll go over a little bit of that shortly. So in terms of the mechanisms of these light-induced defects, we've got the boron oxygen defect, which typically occurs over a time scale of about 48 hours at room temperature to fully form these defects. There's also another defect in multicrystalline silicon that's just become apparent. It's not actually known what this defect is yet. It has a much longer time scale, about 1,000 hours to fully form this defect. You'll see here a graph. Don't worry about this, where this increases again. I'll go over that shortly. But the generation of the defects as the VOC reduces is looking towards 1,000 hours, and it can still be going down. So this means that these multi-modules going out in the field, you won't know about this in a couple of days like you will in the monocrystalline modules. It can take weeks, etc., to fully generate these defects before you get the full effect of the efficiency loss. And all of these carrier-induced defects have increasing potential efficiency losses as we move to the higher efficiency cell architectures like PERC, because as we increase the efficiency, even with the same concentration of a defect, it can have a strong influence on the recombination within the material. So it's becoming more apparent now with PERC. And some of these defects can cause 5 to 10% relative performance losses. So carrier enhanced passivation. So even though the defects themselves are formed by the presence of carriers, there's also a permanent recovery process which is carrier enhanced as well. So even using the same conditions to form the defect, if we leave it for long enough, we can see a permanent and stable recovery of the solar cell. But again, this is going to take over longer timescales, etc. So some of the work, even with modules going out in the field, it can take up to a year for this permanent recovery to occur naturally. And it's not a good thing for panels going out into the field that are going to be producing less electricity than what they should be for a year period. It's going to increase the payback time, etc. So these are certainly becoming more evident in the industry. There's a lot of different theories. We still don't actually know what this boron oxygen defect is. There's a lot of debate in the literature of the actual structure of the defect, and the mechanisms involved in this permanent recovery process has been attributed to hydrogen. I guess that's the theory I believe. There's been other completely thermally based understandings that have come about, so the formation of nanoprecipitates during thermal processing, etc. And certainly some of these need to be considered in a whole range of processes. But it seems more likely that hydrogen is involved, and this enables us to get this permanent recovery. So for some of my work, we've been looking at if these processes are carrier-induced, how can we manipulate the carrier concentrations within the silicon to drive this permanent recovery reaction. So this is a graph that shows theoretical concentrations of hydrogen in a neutral charge state, which has a very, very high mobility, so you can potentially shift to the defect sites very quickly to enable a passivation reaction as a function of temperature and the excess electron concentration in the silicon. And really it's all about the availability of these electrons in determining the charge state of either hydrogen, and it can also change the charge state of the defects as well. So for this change in excess carrier concentration, we've got these parameters that we can play with and use to our advantage. The effective doping of the silicon, the temperature, illumination intensity, and also this lifetime of the silicon, and that's quite an important aspect. As we change the solar cell structure, we change the effective lifetime, we can change the response of the solar cell to these carrier enhanced processes, which can be to our advantage or to our detriment. And then for this theory that basically that even if we have a high temperature process where we have this high H0 concentration, typically it would be lost as we cool down the solar cell. So there's certain optimal paths that we can shift down where we maintain maximum concentration. And it's something important to remember, and it's becoming more apparent, is that the need to cool the wafers quickly in certain processes. Some of it may be completely thermal due to precipitation events, etc., but also for this charge state control, etc. Because a lot of these passivation reactions are two-way. You'll have a defect being passivated by a certain species and also this depassivation process, and we need to minimize that to make sure it's effective. So in terms of the challenges for eliminating LID, a lot of the defects we typically deal with in the solar cell are inherently in the solar cell already, like the structural defects, the grain boundaries, the dislocation clusters. They're always available in the solar cell, so we can attempt to heal them through gettering, passivation, thermal-based processes, etc. One of the problems, particularly for these carrier-induced defects, we take a finished solar cell, so after firing, we haven't actually formed the defect yet. And from what our understanding is, we can't passivate a defect that hasn't formed yet. So first of all, you need this defect formation process, typically this temperature and carrier injection. Then we can bring a species in to passivate it, etc. And then we have our stable process. And we've been doing quite a bit of work around this area. And from what our modelling has shown is really this availability of the defects which limits our ability to eliminate LID in the solar cells. And so a lot of the tools at the moment use relatively low illumination intensities, and it takes quite a long time. And it seems as though the key to solving that is to use substantially higher illumination intensities to actually increase the rate of the defect formation. So we can more effectively get rid of the problem by enhancing the formation of the defect. So this is a little animation on one of our PERC cells from one of our industrial partners that we've taken off their production line. So we're starting off with a VOC of 645 millivolts, and then we start our laser-based process. The VOC drops down, so the PL response drops down as well. And then you start to see the recovery of the VOC as this passivation reaction starts to dominate, and we get this permanent stabilization of the process. And one exciting aspect of our process is that we end up with higher stabilized VOCs and efficiencies than what these solar cells are coming off the production line. Because our processes aren't necessarily just looking at the boron oxygen defect, they can potentially be passivating other defects in the device as well. And so we think the next generation of these LID stabilization tools will be targeting more than just the boron oxygen defect or the light-induced defect, etc. And that's all we have, so thanks for your attention.